Okay, section 2, brightness and the magnitude scale. There are going to be two types of brightness that we deal with when we talk about stars and other celestial objects. The first type has two names, luminosity or absolute brightness. They mean the same thing, they're interchangeable. The total energy a star puts out. Now you'll notice that in this definition, nowhere is distance mentioned. It doesn't matter how far away the object is, the star is, let's say, from the Earth. It's just how much energy that star puts out at all different wavelengths each second. So it's independent of the star's location or motion or anything like that. I like to think about it like a light bulb. How do we know how much power a light bulb has? Well, it's stamped on the light bulb. It's a 60 watt or a 75 watt light bulb. It doesn't matter how close you are to the lamp that light bulb's in. All that matters is that's how much energy it's going to put out each second, even if you're not in the same room with it. Okay, so this is an intrinsic property of the star. It's luminosity or absolute brightness. Well, there's another type of brightness, and that would be the apparent brightness, which, you guessed it, depends on how far away that star is from the Earth. So it's the amount of energy hitting the Earth. And it does depend on the distance, and if you may remember from previous chapters, this little thing called the inverse square law. The inverse square law, there are a lot of things in science that behave this way in nature. Gravity drops off with the inverse square law. That's how gravity changes with distance. It's even how the electromagnetic force changes with distance. And in this case, it's how the intensity of light changes with distance. So the inverse square law is going to be very important here. If you have two stars that have the same luminosity, the same absolute brightness, in other words, side by side they were equal, but if you take one of them and move it twice as far away, it's only 1/4 as bright now. If you move it 3 times farther away, it's 1/9 as bright. 4 times 1/16, and so forth. You should also know how to do the opposite way. For example, if I see two stars, I know they're supposed to be the same brightness, but one of them only appears, let's say, 1/49 as bright in the sky. I know that it must be 7 times farther away. That's how the inverse square law works. That brings us to the magnitude scale. Another way to rank brightness. Now, we have a lot of different scales that human beings have made that kind of match our own experiences and our own senses. For example, the decibel scale. The decibel scale doesn't really work on the normal units of science. The actual scale would be watts per meter squared. That's what you should measure how loud sound is in watts per meter squared. But that doesn't really match the human ear. So we made up a scale. And the decibel scale is based on human hearing. So a 0 on the decibel scale is about the softest sound that you can hear. And a 100 on the decibel scale is at a point where your ears start hurting. Well, we've done the same thing with the brightness of light. We have a magnitude scale based on the human eye. And this all started long ago with a great astronomer named Hipparchus. He lived in the 100s BC. And in the time of antiquity, ancient Greece and Rome, and he actually just kind of went out in his backyard and said, okay, I'm going to rank the stars by how bright they are. So in group 1, he put the very brightest stars, stars like Rigel and Betelgeuse and Vega and Arcturus. And then he went to his next group, group 2, stars like the North Star, Polaris. And he did this down to group 6. And for him, group 6, these were the dimmest stars that he could still see with his eyes. Remember, this is long before telescopes and binoculars and things. So, the modern scale is based on what Hipparchus did. But this makes the scale a little bit odd in a couple ways. First of all, since he put group 1 as the brightest stars, that means that the numbers are kind of backwards to what you might expect. The lower numbers indicate brighter objects. It's a lot like golf. Lower scores are better. That's one way that this scale might be different than what we might expect. But here's the other way. The modern scale, when they tried to kind of force it to fit Hipparchus's original 6 categories, it made it work out this way, where every level on the magnitude scale is actually 2.5 times brighter than the previous level. So a magnitude 1 is 2.5 times brighter than a magnitude 2, which is 2.5 times brighter than a magnitude 3, and so forth. The way you do the math on this to compare different levels is pretty simple. First, just subtract the 2 magnitudes. So if I was comparing a magnitude 3 star and a magnitude 10 star, I would take 10 minus 3 and get 7. Then what you do, once you have the difference, you take 2.5 to that number, to that power. So in that example, you take 2.5 to the 7th power. 2.5 to the 7th power, which is 610 point something. So that means a magnitude 3 star is about 610 times brighter than a magnitude 10 star. So you subtract first and take 2.5 to that level. Now, Hipparchus had 1 star in his level 1, in his magnitude 1, that was actually quite a bit brighter than the stars around it. The star Sirius is much brighter than those other stars in level 1. So in the modern scale, Sirius is actually in the negative numbers. We assign it a negative 1.5, for example. So you can't have negative. Planets like Venus and Jupiter would be in the negative, and of course the Sun and the Moon. Again, it's much like golf. You know, the best scores in golf are under par, so they're in the negative as well. Let's take a look at some of those numbers. We have Sirius there, as you can see, at negative 1.5. Venus, the brightest planet in our sky, at negative 4.4. The Moon comes in at negative 12.5, and the Sun at negative 26.7. That makes it over 400,000 times brighter than a full moon. Here's Sirius. You can see there, if you follow the cursor here, here is Orion's belt, and if you follow the belt to the left, you get to the Dog Star, part of Canis Major, one of Orion's hunting dogs. That's why we call it the Dog Star, and that's Sirius. That's the brightest star in the night sky. Going in the other direction, you can have, excuse me a second, going in the other direction, towards dimmer things, you have a magnitude 6, should be the limit of the human eye. Of course, with light pollution, that's not really true unless you're somewhere really dark. And with binoculars, you should be able to see down to level 10, to magnitude 10. Now, all of those numbers I just gave you are based on apparent brightness. That's the apparent magnitude scale, based on how bright they are from Earth, from standing in your backyard. But remember, there's another type of brightness, absolute brightness. Well, we have a different scale then for that, the absolute magnitude scale. The numbers mean the same thing, but they're much different in most cases. Why? Because we make it fair. With the absolute magnitude scale, you make it fair by lining up all the stars at the same distance. In this case, that distance is 10 parsecs. That's what astronomers chose. 10 parsecs or 33 light years. And when you line it up that way, it really balances things out. It makes it fair. And so the Sun, which is an amazing negative 26.7 apparent magnitude, well, it becomes a lowly 4.85, positive 4.85 absolute magnitude. Because if you move the Sun, in other words, 33 light years away, well, you're barely going to be able to see it at that point. It's going to be a really tiny little dot in the sky. Alpha Centauri is another good example of a star that would be hurt by this because it's 4 light years away, and if you move it to 33, it's going to be much more dim. Some stars would be helped greatly, like Deneb, part of the Summer Triangle. That's a really bright star that's intrinsically very bright, but it's pretty far away. It's still one of the brightest stars in the sky, though. So if you moved it up to 33 light years away, wow, you would probably see it in the daytime. So that's absolute magnitude scale. We'll do one more problem. I kind of did this problem already. Problem 1, you take 10 minus 3. If you compare two stars, 10 minus 3 is 7. Take 2.5 to the 7th power. Boom, you get 610. That's how much brighter it is. This last problem is a little trickier. If you compare two stars that are the same luminosity, okay, they're supposed to be the same brightness, in other words, side by side they'd be the same, but instead one of them is showing up as a magnitude 2 and the other is only showing up as a magnitude 5. The question is, if the first star, the brighter one, is 10 light years away, how far away is the second star, the magnitude 5? Remember, they're supposed to be the same, but it's only a magnitude 5, so you know it's farther away. You know it must be much farther away than just 10 light years. So how do you do this? Well, just talking it through very quickly, you start by subtracting. 5 minus 2 is 3. You then take 2.5 to that third power. You get 15.625, or almost 16. So that means the magnitude 2 star is about 16 times brighter than the magnitude 5. It's about 16 times brighter, but that doesn't tell us the distance. How does that get us to the distance? Well, that's when we use the inverse square law. Okay, so the magnitude 5 star apparently is only about 1/16 as bright. If it's only 1/16 as bright, that means it's 4 times farther away. Got it? And if it's 4 times farther, and the other star is 10 light years away, it must be 40 light years away. That's how you do that. It's a combination of the 2.5 to the x, the magnitude scale, and inverse square law. If you use the exact number, I rounded it. 2.5 cubed is actually 15.625, and if you take the square root of that, you get 3.9 something, 3.95 something, and so the more exact answer is actually 39.5 something light years. If you do it more exactly there with the math. I was just trying to make it a little easier. And that's a little bit about brightness and the magnitude scale. Remember, the lower numbers are the brighter objects in the sky. Thanks for listening.